think you're in. Should be recording.
Alrighty. Hello, everyone. How's it going? Chilling? Yeah. Alright, so we're going to get started with lecture 3. Hopefully it's a little more chill than usual. Here are just some announcements of what's going on. So, Project 2 was released last night. It is called Gitlet, and basically what you're going to be doing is you're going to be implementing the Git version control system on a smaller scale. So hopefully by the end of this project, you'll definitely have an understanding of how Git works, so that'll be awesome. This is supposed to be the largest project of the semester, so make sure you put like your full energy into this because this is the most challenging one, all right? And your partner is going to be chosen tomorrow, so if you're still looking for a partner, just please let your lab TA know, just send them an email, and hopefully everyone can find someone to work with, all right? And remember that both partners need to submit to Gradescope in order to get credit. All right, so both of you need to submit on Gradescope. It can be from the same repository, but you both need to hit the submit button in order to get credit. Make sure you have a token remaining so that both people can get credit. So just kind of paste it out and make sure that that happens. All right. Okay, and also every Friday there's going to be a 20-minute quiz, which you already know. We're going to try to set the time at exactly 20 minutes now, so it's not kind of fluctuating. But yeah, so expect a quiz on Friday. All right, and as usual, there's a live lecture thread, so if there's questions that we can't answer out loud, then you can go ahead and post it, and we'll have people standing by to answer them. Okay, so my part of the lecture is just kind of summarizing what we've done so far and kind of setting us up for the next part of the course, all right? So we're starting to do data structures now, right? We've learned about arrays, we've learned about linked lists, now we're going to learn about all the other data structures. And so basically, this is how you succeed in the course for the rest of the course, right? So what you want to do is, we're no longer focusing on syntax, we're focusing on this variety of data structures we have, and if you want to do it on the midterm, understand like the differences between the data structures and what operations are fast, what operations are slow for different kinds, right? And what are the advantages between using different ones, right? So today we're going to have a case study of your favorite thing, Enigma, right? And we're going to go through and kind of just exercise those muscles and kind of get used to thinking about how like we can think about these data structures and how you want to critically think about them, okay? All right. So, recap from last week, I showed you these very aesthetic pictures. And so here, in the top left corner, we're going to be talking about access from an array, right? So I compared this to apartment buildings, right? If you know the specific address you're looking for, you can jump to that apartment building because all these apartments are the same amount of space apart, right? And they're all contiguous in memory, right? And the analogy I shared with you last time, right? If on the first day of class, if you're looking for 277 soda, right? You started down the hall at 271 soda, right? And then you saw that there's 273 soda, and you're like, where is 272? Well, I guess they're incrementing by 2 every single time, right? So then you didn't have to look at 275 because you knew that's what that was. You could just keep walking down the hall until you hit 277, right? So access into an array is constant time if you know where you're going. But on the other hand, access into a linked list, if you know you want like index 50 in your linked list, you have to hop from one place to another. Just like my terrible time at the airport, right? That airplane is hopping from New York to Seattle, down to San Diego, back to San Francisco. It's just hopping, right? And so if you're looking for a specific index, you still have to traverse the entire linked list in linear time in order to find what you're looking for. Okay, and then on the right-hand side here, we have another operation, insertions and deletions, right? So we saw with arrays, it's going to take linear time in order to insert and delete something, right? That's because, for example, if you want to insert or delete from the front of an array, you're going to have to shift everything over one spot to kind of like cover up where it was, right? So that's going to take linear time. Now with your array deck, you kind of had optimization with that circular structure that kind of eliminated this, but for the raw array, like it's going to take linear time. And then on the other hand, for insertion and deletion into a linked list, if you have a reference to the place where you want to insert or delete, then you can do that operation in constant time, because it's just like putting a sidewalk close sign on the street, right? Like you don't have to close every single sidewalk in all of Berkeley just to make like a deletion of a sidewalk. You just put a sign there and tell people walk over here instead, right? And in constant time, you can delete a sidewalk, or you can delete a node. Okay, so let's kind of use this similar logic to analyze a larger program, right? And so the program you're all familiar with is Enigma. Just a little bit of a refresher, right? So basically, you have all of your rotors here. You put in a letter into the front. So in this case, you're putting in Y. And then it goes through your rotors. And at each rotor, there's a permutation, right? That maps that letter, the input letter, to an output letter, right? So in this diagram, in rotor number 5, in goes K and out comes N, right? And there's just some permutation that's defined by a cycle string, right? And the cycle string is passed into your constructor. And then it goes up to you to decide how you wanted to remember that information so that when permute was called, you can give back the check letter. So a slight little footnote, we're working with constant size alphabets, right? So there's only 26 letters in the alphabet. So technically, anything you did would be in constant time because there's only 26 letters, right? But for the purposes of our case study today, let's relax that assumption and say we have n letters, so a large number of letters. And the question is, if we have a large number of letters, how will our choice in what data structure to use impact our runtime? Okay? Although typically it's not a bad assumption to say, okay, like we have a constant alphabet size, right? So if you're working with like DNA, right, there's a constant alphabet size because there's only A, T, C, and G, right? So there's 4, and so maybe that's not a bad assumption to make. So, but today, just humor me, let's pretend we have a lot of alphabet letters. Okay, so let's try to figure out what our requirements are. What type of data structure do we want to create today? So this is what a lot of you guys did on the project. So I'm calling this string parsing on demand. Okay, so what you do is, in your constructor, you simply take the string cycles and you save it as an instance variable. So you get this.cycle equals cycles. And then you save your string, and now you have access to that string whenever you want. And then, when permute was called, you did this algorithm, right? Basically, what you did was you figured out what index the desired letter was. So, for example, if I was permuting on C, well, C is like over here. So that's like a 0, 1, 2, 3. That's the third character in that example of it, right? And then you're like, okay, I'm going to permute, so I'm just going to get the letter that's next to it, right? So 3 plus 1 is 4. So the letter at index 4 is D, so that's my answer, right? That was the algorithm we did, and that was the best case. But there was a slight problem because what if I called permute on D, right? If I called permute on D, then the correct answer is A. So actually, you would have to backtrack a little bit and go back to A in order to find your answer, right? This is what most of you guys did. And it's not bad because, well, first of all, in order to find the index of where your character was, Java does that in linear time because it kind of searches through linearly down the string and finds where your letter is. And then, in the best case, right, in the best case, if it's just the letter next to it, you add 1 to the index and return. That's a constant operation. But if you're doing this backtracking business, then it could potentially be linear time. And that's because, like, if you had one giant cycle, then going back to the beginning would take linear time, right? So this is what we're starting with. This is our baseline algorithm, right? So we have a constant time constructor because all we did was save the string. And then we had a linear time permute call, right? Because overall we have linear plus constant plus linear. So our permute call is linear time, right? This is slightly not great though, because every single time we call permute, we're paying linear time, right? So the question is, can we do better than that? We can, all right? So here's an idea. Let's parse it once and for all, not every single time permute is called, right? So I think some of you guys went towards this approach, which is better, right? And so the idea is, in the constructor, instead of just saving this.cycles equals cycles, why don't we parse our string there and have a handy way to remember our answer for later, right? And that way, instead of paying every single time you call permute, we just paid once up front in the constructor, and every time you call permute, hopefully that information is more readily available, and you can find the answer in better than linear time. Okay, so this is what you can do. So in your constructor, you can start with the letter A and figure out what it permutes to, right? So you can find A in your cycle string, and you can figure out what that answer is, right? And we just said that that algorithm takes linear time. But you need to do this for every possible letter because in the constructor, you don't know what letters are going to be asked for later, right? So you're going to do a linear time algorithm times n, which is the number of alphabet characters there are, right? So that constructor is going to take quadratic time in order to figure out what every letter maps to, right? So quadratic time for a constructor, and if we can save that result somehow, we have to figure out what that is, but if we save it somehow, then that's good. We paid once in the beginning. And hopefully, if we had a good way of storing the stuff, right, at permute, we can call permute and hopefully fetch the answer in constant time instead, right? And we want it to be constant time because if our solution is requiring linear time, then like we might as well just parse the straight right then and there because that's what our first solution did, right? So we want to do constant so that we're better than before. Okay, so overall we have a quadratic time constructor now, which isn't too great, but now we can desire a constant time permute. Right, and this makes sense because like maybe you're calling permute like 1,000,000 times, right? And so you want permute to be cheap, but the constructor you're only going to do once, right? So it's okay if it's a little more expensive if we're saving a lot of time with every permute call. Okay, here's an idea. Pay as you go. This sounds like a cell phone plan or something like that, right? Pay as you go. And this is kind of called like lazy computing, right? So you only compute the answer when you are asked for it, right? So the idea is that in the constructor, we don't really do anything. All we do is we save the cycle string, right? So we have it for later, and we also initialize an empty organizational system of some sort so that we can return what we need in constant time later. Okay. And so the general idea is when we reach permute, we say, okay, have we seen this letter before? If we have seen it and it's in our organizational system, then we go into that system and get our answer in constant time, right? If we haven't seen that letter before, then we'll take linear time to solve the problem, we'll get our answer, and then save it into our organizational system. So next time, if we're asked the same question, we're going to be smart. We're like, hey, we've seen that before, right? So then next time, it'll be faster, but this time we pick linear time, right? And so this is very similar to before, but we're only going to compute it if we're asked to do it. And once we've been asked to do it once, we're going to remember it so that if we're asked the same thing again later, it'll be fast. Okay, this is pretty good. But the bottom line is that this will be about the same as before, right? So our constructor is constant time because we're not doing anything in the constructor. But if eventually we're going to look through all the letters anyways, then over time, we will be paying quadratic time for all of the permute calls. So in the end, at the end of the day, it'll still be the same, but maybe it's a little better because we've spread out that computation. And this is potentially good because this is kind of like delaying it for later, right? So like if you imagine like Google search, right? Like they probably don't want to predict all of the possible searches you can perform, right? So it's going to kind of do as much setup as it can in the constructor, and then when you're actually going to perform a search, it's going to do the remainder of the work right then and there when you ask for it, right? It's not going to pre-compute everything. So this is potentially not a bad idea, but I think for what we want to do, it's probably better to use the one that came before this, right? Oh no, this one, right? Let's pay once and for all because I think we can do better than quadratic time here, right? So if we can do better than quadratic time here, and we still have constant time permute calls, I think that would be the better solution. Okay, so I think we've kind of played around a little bit, so we know what our ideal data structure is going to look like. So we want to have something that is linear time in the constructor, right? Because we had quadratic before, and we know that's possible, but I think we can do better than that. Let's try to aim for linear, right? Can we get constant time in the constructor? Well, maybe, right? So we can do what we did before. We can just save the string cycles into a field and compute it later. But that's not what we want. We want to compute everything up front in the constructor. And so linear time is the best we can do because there's no way you could do all this pre-computation. Like, you can't solve this problem without reading the string at all, right? So you have to at least read the string in linear time in order to have some setup. So linear is actually the optimal runtime we can hope for the constructor. You have to read the string in order to do it. But then for mute, we say that constant time is our desire, right? Because if we had a linear time solution, well, we might as well just do our very first thing that we did and just parse the string and look for the index, right? So we want to do better than linear time and mute. Let's try to do constant time, right? So this is our goal. We want to do linear constructor, constant permute, and what we had before with our compute everything up front, right, was we had a quadratic constructor and a constant permute, right? So let's try to see if we can do better than this. Okay, this is proposal 2, a linked list of linked lists. You saw this on the midterm. Okay, so in case you don't remember, basically the idea was we created character nodes for each of the characters, and we kind of linked them together in a cycle, right? Depending on each of the cycle groups, right? And then we linked each of the cycles together with a cycle node. Okay. So, right, just a little refresher. I know you don't want to be looking at this yet, but there's this picture here, right? So, for example, ABCD, we had each of the characters, and they're pointing in a cycle. So each one's next is the next character, and you can just find the node you're looking for and get the .next item and return that as your answer. And then all of these character nodes are in a cycle, and each of these cycles are linked together by a cycle node. Ooh, okay. Cool. So how fast was the constructor? Here, this slide says it's linear time, right? And so let's double check the code. So you can kind of tell by the skeleton that, yeah, it's going to be linear time, right? Because here, we have one for loop. And what this comment says is that this for loop, make it a little bigger, right? What this for loop does is it goes through one cycle at a time, all right? And then we have a second for loop here, which you can probably guess is going to go through the letters in that one particular cycle at a time, right? So basically, all we're doing is we're traversing each letter in the cycle eventually throughout this algorithm. And so that's going to be linear time because we're touching everything just once. Okay, so linear time constructor. How about permute? Well, it's also going to be linear time, right? Because what we're doing is we're going to basically infinite loop, and we're going to keep looking until we find the letter we're looking for. And once we find the letter we're looking for, we're going to stop and return the answer. So in the worst case, we're going to have to look through everything, and we'll find what we're looking for. So that'll be linear time in the worst case. Okay, so this is what we have. This solution is linear and linear. So it's actually not that great. Okay, here is another proposal. Let's try using trees, right? Because we learned about trees in the last slide, right? And this is kind of like the process you want to go through when you're like solving exam problems. You're like, okay, like what have I learned? Okay, we've learned about like linked lists, so I'll try that. Learned about a tree, so we'll try that too. Like, just kind of go down the list and try everything and see what happens, right? So let's try trees, right? So for the constructor, what you can do is you can kind of make like a map, right? Because each letter maps to another letter. So you can design a node such that like it has one field which represents the actual character and has another field which represents the letter it's supposed to go to, right? So these are just two instance variables in the node, right? And you can kind of design a tree like this. So you have this one that is the character, and that's called the key. And then you have the thing that it maps to, which is called the value, right? So that's just terminology that we use for mapping a key and a value pair, right? And so you can make nodes out of this, and you can just dump everything haphazardly into a tree like this, right? I just kind of drew nodes and arrows wherever I wanted, right? And I can construct this in linear time, right? Because I can manufacture my nodes as I see them in my cycle string, and I can just dump them wherever I want that's most convenient, but I'll read through the entire cycle string, and I'll construct this. Okay, so how long does permute take? It's going to take linear time because I just haphazardly dumped everything wherever, right? This is a mess, right? Like trying to find like clothes in a messy room and your clothes all over the place, right? You don't know where stuff is, right? And so basically, it's going to take a linear time traversal to go through every single node and find what you're looking for, right? So you can imagine, like if this was a linked list, we'll just have to search the entire linked list because we don't know where it is, right? Here, it's a tree, so it's a little more tricky to jump around. But if we had a way to go to every node, like we would have to look at every node, right? And so actually tomorrow in lab 9, you'll learn all about traversal. There's many ways to traverse the tree. There's many ways to go touch every single node in this tree. More ways than you can possibly hope for, but basically at the end of the day, it's going to take linear time. You have to look at it.
Okay, well this is kind of dumb because like we put in so much work to make a tree, but it's like the same runtime as like before, right? It's the same as our linked list of linked lists. So there's one thing we haven't taken advantage of, which is like there's a tree structure. Let's try to use the structure to organize what we're looking for, right? Like we have shelves for our clothes. Why don't we put clothes in an organized fashion into our shelves, right? Because right now we just have random clothes and random shelves. That's not good. Okay, so we can do something called a binary search tree, right? So you learned about binary trees. Binary tree, the word binary means two, right? So every node can have two or less children, right? And then the second word here, search, means that there is some organizational system to it, right? And so the idea is this, right? If we have the letter D at the top, then everything to the left of that node is going to be less than that value, and everything to the right of the D is going to be bigger than that value, right? So in this case, I'm using less than and bigger than as in like alphabetically, right? So here, everything on the left side of the tree of the D is like less than it, so we have A, B, and C, and everything to the right of it is bigger than the E and F, right? And this rule is going to have to apply recursively, right? So if you look at node B, like to the left of it is A, which is less than it, to the right of it is C, which is bigger than it. So everything needs to apply recursively. Okay? And if you have this, then, well, it's going to take log linear time in order to put this together. Why is that? If I have a new node, I'm going to have to like traverse this tree to the bottom, right? And then figure out where I want to put it. But because this tree is organized in such a way, if I choose to go left here, I've basically thrown away like half of my possibilities, right? And if I go to the right here, I've also thrown away half of my possibilities, right? And so because every single time I'm throwing away half the possibilities, that sounds like log to me, right? Which is why it's log. And there's n things to insert, which is why it's n times log, right? Okay, similarly, to find something, if I'm looking for the letter C, I start at this D, and I say, okay, I'm looking for C, so C is less than D, so it must be on the left side or it's not here at all, right? And when I go here, oh, it must be to the right of B or it's not here at all. So if I'm looking for something, it's also eliminating half the possibilities at every move, and so it's going to be log time to find something I'm looking for. Okay, but this isn't an ideal situation. This is also a valid binary search tree, something like this, right? I have F at the top, and E is less than F, so it goes to the left, and D is less than E, so it's to the left, and C is less than D, which is to the left, and D is less than C, right? So this is a valid binary search tree, but it looks like a linked list to me, so that kind of sucks, right? And so we kind of, in this worst case situation, have the runtimes of a linked list, right? And so we call this a spindly binary search tree, just everything's leaning to one side, or it just looks like a linked list, right? And we basically have the behavior of a linked list. So instead of this log linear time, n log n time, we have quadratic time, n squared, because to insert something to the bottom, I have to go through all n items just to reach the bottom, right? So we basically have a linked list. This is terrible, right? And similarly, like our permute's no longer log time. It's going to be linear time to find something. I have to look at every node. I can't eliminate half of the items at every move. Okay. So this sucks. After all this work, it's still possibly bad. But we can have something called a balanced search tree. So a balanced search tree basically maintains its balance on its own. You're going to learn about that more in Lab 11. But basically, it's going to ensure that it looks like the tree on the previous slide where everything is well balanced. And so we'll have the same runtimes as the previous slide because it's a self-balancing tree and you won't have something that's like this. Okay. So binary search trees, right? Again, binary means two or less children for every node. Search means it's organized in this left-right fashion. Balanced search tree means it's self-balancing, right? So binary search trees would be lab 10, balanced search trees would be lab 11. And note when we say BST, that means binary search tree, not balanced search tree, even though they are both BST, right? So BST means binary search tree, okay? Okay, so summary of what we've done so far. So our string parsing system, right, is quadratic and constant. Our linked list of linked lists was linear and linear. Our binary search tree, if it's spindly, it's basically like a linked list, so it'll be quadratic and linear. And then if we have a balanced search tree, then it'll ensure bushiness, that's the opposite of spindliness, right? Then we'll have log linear and log. Okay, so we're getting close. You're starting to get bored. Let's talk about one more. Okay. This is what some of you guys did, or something, you guys probably did something similar to this. Let's keep an array of nodes containing the mappings. Okay, so in the constructor, initialize an array of length n, so you have one space for every character of the alphabet, right? And you can tell based on like what letter number it is in the alphabet, right? So for example, if I'm looking for C, that's like A is 0, B is 1, C is 2, so I can just look in the second index and find what C is supposed to map to, right? And remember from the first slide, access into an array if we know what index we're going to is constant time, right? So this is really good. So our constructor is going to take linear time because we're going to take linear time to read the cycle string, right? And then we're going to take linear time to basically fill in each of the n items into our array, right? Each of those fill-ins is going to be constant time because we can jump to the right place and fill in the answer in constant time, right? Multiplied by the n things we're reading in our cycle string. So constructing this array is linear time. And permute is constant time because if we know what letter we're looking for, we can jump in our array to the right spot, look it up, and return it in constant time, right? So this is actually a very good solution. So we have achieved our goal. We wanted linear and constant, and we have linear and constant with this last solution. There is a very small problem, and that's if our cycle string is sparse, right? Because remember there's this rule that if a letter is not specified in the cycle string, it maps to itself, right? And so maybe it's sparse, as in like the cycle string isn't very long, but there's many letters in the alphabet, right? So for our array, like we would still have to allocate n spaces, one for every spot in the alphabet, but there's not many mappings to keep track of. So it's kind of wasteful in that sense. Like we're wasting a lot of storage space. And so there is a solution to that. Basically, instead of saying, okay, index 0 is A, index 1 is B, index 2 is C, like let's just have a magical system that tells us, given a letter, what index am I supposed to get into, right? And so this special thing is called hashing, and we'll learn about that a little later, but that's just kind of the secret. So basically this last approach, we're very close to what a hash map actually looks like. If you just implement hashing, then it will be basically a hash map. All right? So I think that is the end of this section. Is there any like questions about like data structure analysis or program analysis or anything like that? Yeah.
Do we treat memory storage space and runtime with the same priority or more importance, or is one more important than the other?
Right, so the question was like, what's more important, runtime or storage space, right? And it depends on your situation. What is cheaper, right? What can you afford more of? So kind of in the modern day and age, like runtime is like, it's valuable, but we can always throw more hardware at it and make it run faster. But maybe we're running out of space to store stuff because everything's like big data, right? So potentially, like runtime is better. But in other cases, maybe storage is more important. Like if you're trying to limit the amount of information you're using or whatever like that, like you don't want to redundantly store things if you don't have to, right? Then in that case, runtime might be more important. So it just kind of depends on the situation, and that's why it's like there's no like hard truth, like always use this data structure, right? It depends on the situation and what you think is more important. All right, cool. I'm going to pass it on to Jackson now, and we're going to talk about abstract data types.
I get this clipped on, so I don't have to hold it. It's gonna work. All right, can we hear me? No? Yes? Yes. Okay, I think we're good. Okay, cool. So I'm just going to talk a little bit about abstract data types. So this is just something that we're going to come into contact with more as we go through the course. So in the beginning of the course, we kind of had, linked lists and arrays, and those were like concrete things that we like know the rules of and we're able to work with. But like as we were introduced to the idea of a linked list, we were then introduced to like how to do it like a singly linked list, and then the sentinel nodes, and then doubly linked lists and stuff like that. But at its core, all of these things are like the idea of a linked list. Whether or not they all work exactly the same way isn't that important as much as just understanding the basic principle of a linked list. So in this section, we're going to talk more about other conceptual ideas that appear in Java and in the code we're going to write, and how to use them as data structures. So the first thing I want to talk about is just the idea of interfaces and implementation. So as we remember, there's this thing called a deck, which I hope you're all familiar with at this point. But we developed this idea of an array deck and a linked list deck, and both of those were types of deck, right? So we made this interface deck, and then we took our array deck and our linked list deck, and we made sure that they both followed this set of rules that deck set aside, right? So in a deck, you have to do certain things, and we took an array and we used the backing structure of an array to make it do those certain things so that it looks like a deck, and we took a linked list and we made it do those certain things so it looks like a deck. So if I'm a user and I'm using the array deck or the linked list deck, whichever one of those I'm using, I don't actually have to know what's on the inside as much as I just have to know that it works like a normal deck. So you as the programmer know what the guts of the deck look like, but I as the user just think of it as this abstract idea of a deck. So this kind of abstraction barrier is what we want to get at for the rest of the course. Of you don't really want your user to know what all the insides of your program looks like as much as you just want it to behave as they would expect it to. So abstract data types basically overall are just defined by their operations and not by their implementations. So as we saw with the deck, the interface for it has to have all of these different things, and you don't actually, like when you made the interface, you didn't have to define any of the methods or any of this information. We did, however, use the default method for isEmpty because we know that an empty deck has size 0. So we were able to use the fact that interfaces in Java are now able to have default methods, and we're able to fill that in. But for the most part, we just said, here's this idea of a deck. A deck should be able to do those things. How it accomplishes these things depends on the implementation. So that's the difference between the interface of the deck and the actual implementation that you performed. So we saw that the array deck and the linked list deck were both implementations of this deck interface. Cool. So moving on from that, similar to a deck and how that's something that's kind of like this abstract idea, we have this idea of a stack. So a stack is an abstract data type which supports these following operations as well as a few more. But basically what you want to be able to do with a stack is you want to be able to push items onto the stack, and then you want to be able to pop them back off of the stack. So the way that I always explain a stack is if you think of it like if you have a box and you have a bunch of papers, right? Now I want to stack papers, right? Everyone's experienced that, hopefully. But as I put the first paper in the bottom of the box, that's at the bottom, and then when I put the next paper in, it goes on top. So if I want to reach in the box and pull a paper out, the first one I get out is the last one I put in. So if I stack papers, like the first one at the bottom, then the second one, the third, all the way up to 100 papers, if I pull them out, the order that I'll pull them out is the 100th paper, the 99th paper, all the way back down to the first paper. So it's kind of like this reverse idea of when I stack stuff up and I want to take things off one at a time, I can't pull anything out from the bottom, or maybe I'll rip my papers, and that would be sad because most of the things I'm stacking these days are midterms, and you don't really want that getting ripped out. So the way it'll work is if I want to put items in, say I put 4 in, and then 6 in, and then 2 in, as I pull items back out, I'm going to first remove 2, then 6, and then the last thing left would be 4. And so this is this abstract idea of how a stack would work. But the question is, could we use information that we already have to implement this stack? So here I have a question for you and you can go to this Yell key at the top, and if you go to this URL, then it'll come up with a Google form that you can put in. But can you decide amongst yourselves, I'll give you 30 seconds, which implementation do you think would result in faster overall performance if you wanted to create this idea of a stack? Should you use a linked list, or should you use an array? You can talk about it with a neighbor and figure out which one you think would be better, and then you can vote. Oops. Alright, so let's bring this back around and let's think about why we got the results that we did, right? So it seems like a lot of people think that the best way to make this stack work is to use a linked list, whereas a minority think an array. Anyone who had the linked list idea, can you explain why it might work? Yeah.
Since the main operations are adding and removing, you can set a pointer to the top and rearrange the pointers. Instead of an array where you might have to push and resize it.
Yeah, so the idea is like you can just have a pointer to the thing that you want, and then with an array you might have to resize and move stuff around, so that might not be so great. Did anyone say an array might be better? I know someone did. It's on the proof. Yeah? Anyone? Okay, maybe no one said an array would be better, but I tricked you. They both work. So the idea is that we can use both of these ideas and use pointers in either case, right? So with linked list, we can basically have our whole linked list, and as we put stuff on, we can send items to the front, and then when we want to take items off, we can pull them back off from the front. So as I put like my papers on, they get added to the front, to the front, to the front, to the front. That pushes that first paper all the way to the back, and then I can pull off from the front until I get to that last paper. With an array, I can do something similar, where I can just keep adding in the array and just have a pointer to that last thing I added, and every time I remove, scoot that pointer back. So it should work the same with either of them. There's a little bit of a difference in both cases, but basically in a linked list, you're not going to have to resize it, so maybe it'll be a little faster. But again, in a linked list, you have a bunch of objects linked to each other instead of just a block of memory, so maybe that'll slow you down too. So there's a trade-off in either way. Okay, so other things to note about the stack. Although this idea is abstract and we just came up with 2 ways to implement it, Java actually has a concrete stack class, which happened in Java 1.0, which inherits from this thing called a vector that you don't really need to know about. But what this means is in Java, if you want, you can make a new stack by saying like new stack and it'll work. You don't have to like implement it or extend something in order to get it to work. You can just do it. However, the official documentation states that you should use a deck instead, because the deck can do more things than just a stack. So you're actually kind of ahead of the game because you've already been able to figure out array decks, and those people who came up with Java had to like make this whole like nasty stack thing that they decided they didn't like. So congrats. But yeah, so as you see here, you've got like you can make a deck, call it a stack, and then have it be an array deck. Cool. So that's the stack. Any questions on how the stack works or anything about that for now? Cool. Here's another one. Let's talk about the queue. So this is similar to a stack, except this one we're gonna like put things in and pull things out in a different order. So it has the following operations, and you have to be able to offer items to the queue, and then you have to be able to remove items from the queue. And instead of a stack where the last thing you put in is the first thing you get back out, it's gonna go in like the normal order that you'd expect when you hear the word queue. So it's like lining up, right? If you get in line somewhere, you expect if you're the first one that got in line, you should be the first one to get served. Same idea. So if I have 4, and then I add in 6, and I add in 2, 4 comes out first, then 6, and then we're left with 2. So now that we've had this like flipped data structure, I have another question for you of which one should we use, the linked list versus the array, to implement the queue. So same thing as before, but this time we want to flip it and go the other direction. So take a few moments to discuss, come up with an answer. I won't trick you again, don't worry. so let's talk about this one. So we're getting more of an even split on this one, linked lists and arrays. So let's think about what the answer might be. Who said array? Who said linked list? Who didn't feel like voting? I see you. So yeah, like I said, I wasn't going to trick you again, but I lied. I tricked you again. So they're both pretty much going to work the same. And the idea that we can still use these pointers, right, that we came up with before. And like, so with some sort of like linked list, right, even if we're putting things on the front, we can have a pointer that points to that last item. And then we can always like drop it back bit by bit, say using something like, I don't know, a doubly linked list. Using our deck idea. Ooh, I almost tripped. That would have been bad. And then same thing with an array. We can just always have a pointer to the front and pull off that way. So in either case, whether we're using a stack or a queue, we can still use these ideas that we've come up with, say in a deck, and have pointers to the beginning and the end. And in that way, we can fetch items from the beginning or the end, depending on whether we want to act as a stack or a queue. So fun facts about the queue. In Java, there isn't a concrete queue class, so if you want to use a queue, you have to make one yourself, because it was added after. So what happened was after they had made the stack, then they came up with this thing called a collection, where they were like, oh, collections are good. It's like where you store a bunch of things. And then they thought, oh, a queue is a good idea for a collection. And then they thought, oh, wow, we really messed up with stack. We probably shouldn't have done what we did. So we'll just, put a Band-Aid on it and move on from here. So a queue is an interface, whereas a stack is an actual class. But what that means is if you want something to act as a queue, you'll have to create your own class or use another class which implements it. However, we do have a couple classes that we know already which implement it, which are the ArrayDict and the linked list. So you can already use those as a queue, which makes life easy. So if you want to get that behavior of putting things in the front and getting things back out the front, then you'll be able to use either of these. Cool. All right, one more time. No more tricks. So this is another abstract data type that I want you to think about. So those other ones, worked a certain way and they were pretty similar. This one's a little different. So here's the idea of a grab bag. So what this is I want the following operations. I want to be able to put things into the grab bag, which is just something, right? And I want to insert items in, and I also want to be able to remove items. But I'm going to remove a random item from the bag. And then I also want to sample the bag, where I sample a random item from the bag without removing it. So it's okay if you don't know how sampling works exactly, but I just want to take one single item out of the bag at random with equal probability, but I don't want to remove it, or I want to remove it. So remove takes it out, and sample just looks at it. And then I also want to know the number of items in the bag. So based on these things, which implementation do you think would result in faster overall performance? You can go ahead and vote now. And talk to a neighbor if you don't get it. Okay, so let's bring it back around. And so for this one, it looks like a lot of us really like the idea of using an array. Exactly 3/4 of it. Oh, someone just voted. All right, never mind. That's fine. I'm glad you voted. So why did we want to choose an array versus a linked list? Does anyone have an idea? Yes. Yeah.
access for the array is much faster.
Yeah, right. So then which of these operations are the ones where we care about that? Like which one's the important one?
Remove and sample.
Yeah, right. So what we'll do is if we want to remove or sample like random items, we're going to have to choose a random item in there, right? And if it's a linked list and we know the size, we can choose a random item like within 0 up to that size. But then we have to go find that item in there, and that'll take linear time to like scoot through depending on what that random number we came up with was. With an array, we can generate that random number and then immediately access in and then pull it out. So it's a lot easier to sample from the array. So already we're thinking of ideas of how we can use like the different data structures we know to come up with different like abstract data types, right? So we want to take these abstract ideas and figure out ways that we can implement them and have them run smoothly and efficiently so that a user using this would have no idea if there's a linked list or an array and doesn't really even have to know what the linked list or an array are in order to use a grab bag. So part of the idea of what we want to do in this class is say, okay, here's something that we want to achieve, here's a set of requirements that we want to like obtain, and then the implementation is up to you to make things fast, efficient, and really clean. So yeah, in general, like just to talk a little more about abstract data types, there's a little bit of a syntax differentiation between the data types and the implementations. So things to know, as you saw already, is that interfaces in Java aren't purely abstract, as you can have some implementation details, like that is empty in our deck interface, because you can have default methods. But so as an example of like how to use an abstract data type versus implementation, you can declare a variable with its abstract data type, and then you can actually have the implementation of like what it's instantiated as, and that's the implementation type. So in this case, we know that this deck D, when it's like called, because it's like static type is a deck, we won't be able to use that cool get recursive that we had in the linked list deck, because any like deck doesn't have that method when we use our method lookup. But we know that D's type is a deck, so any of the deck methods are available for us to use. Okay, any questions on this so far? Cool. Okay, and so I mentioned collections earlier, and this is just one of the really important interfaces in Java, and a lot of the interfaces that we'll be using extend this one. So a collection, like a lot of things that extend collections are like, we have lists, right? So a linked list and an array list and other types of lists are collections. And then there's sets of things. So if like you know what a set is, you can only have like one of each element in there. You can't have duplicates, and that's a type of collection. A collection is just something that holds other things. And then something that Matt was mentioning earlier was the idea of like mapping between items, where like we have permutations in Enigma, or I can map your name to your midterm, which is like, if you've done anything in Python, you know like a map is pretty much the same thing as a dictionary. But lists and sets and maps are all like things that implement this collections interface, which is it lets us look through the items and like iterate over them and obtain things and like look at things inside of them and remove things. So it's just a lot of abstract ideas that will start to come together as we get concrete implementations. So as an example of like how maps work and things we can use it for, like as Matt was mentioning before, you can map like characters to other characters if you want to do something for Enigma. You can also map pretty much anything that you want like some associativity with. So if I had some sort of like sentence and I wanted to map and see how many times each word appears, I can go ahead and map it this way. So if I have like help, I can't code, I need help. Then if I turn it into a map of like how many times each word appears, I'll see that help appears twice and I appears twice. And the other words just appear once. But what I'll do is like to create my map, as I go through the map, I'll say, okay, I'll look for that thing in the map. If it's not there, I'll create a spot for it with a counter of 1, and if it's already there, I'll just increase the counter. So this is something you can use a map for, and then now we have some concrete version of this map interface. So as a interface, we have map up here, that's our abstract data type, and then what Matt was getting at before was this idea of a tree map, where we have like good access time, but that's the implementing class. Okay, any questions on this? Like a quick crash course on maps-ish. Cool, okay, good for now. And then just in general, the Java libraries have a bunch of useful interfaces and implementations that you can use. So collections That's a collection is an interface, list is an interface, set is an interface, and map is an interface. So you can't use those, but you can use the ideas that they put forth, and you can actually use a concrete linked list, array list, hash set, tree set, hash map, and tree map. And those are things that you can actually instantiate new versions of, and you can use those in your code to make it faster. So theoretically, in Enigma, you could have made like a hash map or a tree map to control all your mappings, which gets to some of the timing requirements that map is trying to get to before. Okay. Anyone want to take a break? You want to take a break? Or did you have a question? Okay, break time.
Okay, so your break is 3 minutes long now, so I'm not assuming what will miss you.
everyone. Welcome back. So now we're going to switch gears completely and talk about the thing that just got released this morning, actually, which is Project 2 Gitlet. This is actually one of my favorite projects I've ever done, so I'm really, really excited that we're choosing it as the project for this semester. Okay, so just as an overview here, Matt kind of talked about this already. You will be implementing your own version control system based off of Git. So you guys have used Git this whole time. Now you'll be creating your own version called Gitlet. In this project, there was going to be one big difference between what you've done before, and there will be a very involved design process, more than what you have seen before. So it'll consist of a design document and a design review with your TA. So John here is actually going to talk about that in a little bit, but you're going to have to take part in these two things in order to make sure that your design is good to go. All right, so you're going to have to do this in a partnership, just like we did in the past assignments, in the past projects. You'll be given a new repository, the SU19-Project2 repository. So just make sure to add your partner on the partnership page once you figure that out. And the autograder and master thread should be up by the end of this week. All right. Okay, and just as a overview of all the deadlines, so there's just this project is pretty long. Like Matt said, this is one of the largest ones. So here's just like an organized way to see what is happening. So currently we're on this Wednesday right over here, and we're doing our Git and Gitlet overview. But tomorrow, make sure that you have committed to your partnership. The day after, we'll have signups for you to sign up for your design reviews. So one thing I didn't mention is that the design reviews, they'll be occurring during lab on Monday. So you'll sign up for a time slot. You'll just show up during that time slot and talk with your TA about how your design is working, and John will talk about that in a little bit. But the signups will be released on this day. The design docs will be due on this day, and then the design reviews will be on this Monday. Right, so we're going to have 2 project work days following that. So in lab, you'll just be focused. So in lab, you'll just be focused mostly on just doing the project that day, being able to ask your TA any questions that you have, and being able to work with your partner in lab so you can get your questions answered really quickly. All right, so now let's go into what is a design doc and what is a design review even. So John, let's come on up. So this is John, he's one of the TAs. I think he teaches the 11 to 2 p.m. section. So
All right. Hello, everyone. Can you hear me? Should I speak louder? All right. All right. I guess I'm gonna just hold it like this. So, all right. So we're gonna talk about design docs and design reviews. So this is a topic that's very near and dear to my heart. You'll find out why in like 2 slides. But what we're gonna do? Well, I guess this is my hello world to this class. So if you're not in my 11 to 2 section, hello. My name is John. This is who I am. So this is me. I did Gitlet 2 years ago as a student. Last summer I taught it, and I think Gitlet is a great project. So I still include it on my projects list. So next to Bobabot and the 162 project, Gitlet is still there. So this is a good project if you ever want to talk about an interview or something. But more importantly, why am I the one to be talking about this? Well, I also teach 162. So if you look, there's me right there when I had long hair. Yeah, so this 162 does design docs and design reviews. So 621B has kind of tried to do it for the past 2 summers. It was kind of informal. It wasn't that helpful. But now Christine and I are working to make it more rigorous and helpful to you. So what will we be doing in 61B design docs? So the reason for design docs is to plan out your code before you start coding. So it's essentially having a roadmap so that you know what you're doing before you try to do it. So if you're going into a dark tunnel, you probably want to know the layout of this dark tunnel before just running in and feeling around and touching a spider or something. So this is one way to help you do that. Another reason is that it helps us to read your code better. So lots of problems in Gitlet have to do with your conceptual misunderstandings or conceptual problems with how Git works, and it's much easier for us to debug your ideas than your lines of code with red squiggles all over. So this design doc will help us to read your code and figure out where you can improve, how to fix things, and it's a way for us to catch these problems early on before you commit to like writing 2,000 lines of code and then your TA telling you this is all wrong. So this will help you not experience this. Design docs are also very widely used in industry. So if your manager tells you do this thing, instead of you writing, again, 2,000 lines of code, them telling you, I didn't ask for this, I wanted this other thing, instead of committing to this one design, you essentially write down what you're gonna do, you show it to your manager, they're like, all right, sounds good, go do it. And now you have a pretty good guide of what you're supposed to do or what to change before you actually start writing your code. You can also prepare for 162. So this is my shameless plug of this class. It's a really good class. And I can assure you that after doing this, out of every single student coming out of regular 61B or 61BL before, you all sitting right here are going to be by far the most prepared. Does that mean you should just go straight into 162 after this class? No, please take 61C, otherwise you're going to get stomped. But you'll be really prepared when you get there. So. Okay, that's enough about all of this. What is your design doc actually going to look like? So the first section is going to be your data structures and functions section. So here you're going to essentially just declare every single thing that you're going to make. So all the classes that you're going to make, all the fields that are going to be inside these classes, and all your most essential functions should be in this section. So do we want a listing of every single thing? Not really. Just pick kind of the most important ones that you want to show us, or the ones that you're kind of concerned about, and the ones that are most crucial to your design. So do we care that you're declaring I to do a for loop? Not really, but do we care that, let's say this is an example from Enigma, do we care that you have a forward and a backward array? Maybe. So this section is where you're essentially just saying, this is all the stuff that I'm going to be working with, and this next section is the algorithm section. So this section is where you tell us how everything fits together. So if you're going to make a commit, if you're going to do a merge, if you're going to do any of those things, this is where you explain how you're going to do it. So you reference everything you made here. So maybe you have a commit class. So how does the commit class algorithmically store itself? How does it interact with other commits? All of that. So that's all going to happen in your algorithm section. Again, we don't want code, we want a description of how you would do something. So instead of writing out a for loop, you'd say, iterate through all of these things, and then do some sort of work. The next two sections are arguably where you have the most creative freedom, and is where you're kind of, this is more of a conversation with your TA of, this is how I'm doing it, and this is me proving to you that it's correct. So our next two sections are persistence and rationale. So persistence, for Gitlet especially, it's important to make sure that your state is saved between every command. So in the labs and in your previous projects, every single time you ran a program, it would continue running until the very end. So what's different about Gitlet is you run Gitlet once, it stops running, and then you run it again, it starts running, and it has to remember where it was before. So in this persistence section, you have to tell us how do you ensure that it starts up where it left off last time. So it should save all your classes, it should save your commit tree, it should save all of that for you. There's lots of different ways to achieve this, and this persistence section is for you to explain to us how you're going to do that. And this last section is rationale. So generally there's, so this is where you're going to be using your big theta, big O, big omega here, and proving to us that the algorithms you chose and your persistence will meet our runtime requirements. So is there a requirement for runtime? Well, it can't be infinity, but it should be reasonable. So if you prove that your algorithms meet this certain runtime requirement, then we are all good. Generally, there is runtime requirements that are or runtimes that are better than others. It's not two have the exact same option and they're equally good, like what Jackson did 3 times to you. Generally, there is a good solution, and you want to find it. And when you do find it, you want to explain how you got to there. So this rationale is just for you to explain how did I get to my solution and why is it better than everything else we considered. Okay, so that's enough about what it is, but what does a good design doc look like? So we don't want your code. We don't want like this spec again. We just want you to get to the point. We want to hear what you're doing, how you're going to do it, and be very clear and like make it easy to read. So after the TAs have read like 15 of these design docs, like we're tired. So make it easy to read for us so we don't like open up a blob of text and we're like, oh my god, another one of these. So use numbered lists, bullet points, anything to make it readable, and it'll go much smoother for all of us. And yeah, that's pretty much it. The general question you want to be asking yourself at the end of your design doc is, if another student were to read this design doc, could they build my project exactly? So if you're missing something important, you probably want to put it in. If you have too much, like let's say like you have too much and you're running out of space, you might want to cut those extra things out and put in like the important stuff. Okay, so after you write your design doc, your TAs are going to read your design doc and give you feedback in the form of a design review. So this is a really serious time. Do not treat this lightly. The 162 staff especially, if you come late, we take off like 50% of your grade. So I don't know if Christine wants to be this mean this time, but understand that this is very serious. You have like 10 minutes of you talking with your TA about your design. And then what we'll cover is like how your design looks, what you might need to fix, what you might need to elaborate on more, and then we'll probably grade you in some way. But we're definitely going to be more lenient than in 162. So you have that going for you. So that's pretty much it. So since this is my like one time to shine and lecture, I'll stay around for a bit if you have any questions. I'm going to plug the two classes I taught, 61C and 162, if you ever have questions about those. I'm here. Also, the people who have not taken 61A. I have not taken 61A either, so E7 people, I'm here for you. Okay, that's enough, yeah. All right, here you go, Christine.
All right, okay. Thank you, John, for telling us all about those design docs. Just wanted to let you know that this information is in the spec as well. So if you go into the design review and process part of the spec, there's a link that has all this information there too. So you can see it in this format. You can also see it on the spec as well. All right, so for the last like 40-ish minutes or so, I'm just going to be talking about Git and Gitlet. So the things that we're going to first talk about is just how Git works in a little bit of a lower level than you might have seen before, which will be pretty useful to when you're trying to implement the same things in Gitlet. After that, we'll talk about the more specific Gitlet-related things, such as persistence, like John was talking about, and some other stuff that's probably in there too. All right, so remember that we have this version control system. It's called Git. Whenever you add and commit something, Git will take a complete snapshot of that file. Right? It takes a picture of it, and it'll store it wherever it stores it. So Git will think about the history of your files as basically a stream of these snapshots, and will allow you to retrieve any snapshot that you've ever made before. So remember that checkout command. If you've ever made a commit before, you can check out back to that snapshot that you took before. So here is a kind of visual representation of what Git does. So different versions can be different commits. It has all these files in here. So these are all different snapshots. And the dotted ones right over here represent snapshots that persist through different versions. So version 1 has file A, B, and C. Version 2 has changed file A and file C, but B has stayed the same. And then so on and so forth with 3, 4, and 5. But this is essentially what Git does. It takes snapshots and then it lets you go back and forth between all these snapshots. All right, so remember that permanently backing up a file involves both adding and committing. Only adding, we'll see more in a little bit, but adding will only do half of the work. So remember that you have to do both to permanently back up your files. Okay, so there are really a few moving parts in the whole Git repository thing, so I thought I'd break it down right over here for you. So there are three parts: the working directory, the staging area, and then the actual .git directory. So we'll start with the working directory. This is where you will work on a given version of your project. So for example, you work on your lab, like lab 8, you'll work on project 2. Those are all things that are inside your working directory. It's what you have access to and what you will be changing. All right, the next thing is the staging area, and this is what stores the information about what will go into your next commit. So whenever you type git add something, that will put that snapshot into the staging area. So that will be what will be put in the next commit, right? So the staging area is the intermediate place between the working directory and the .git directory. And lastly, we have the repository itself. So that's the .git. It's usually hidden from you, so you don't normally see it, but it'll store all the metadata. It stores all the snapshots that you've taken. It stores all the commits that you've made. And it stores everything else that you'd ever need to know about this repository. Okay, so we're going to be talking mostly about the staging area now and seeing how the commands that you normally use will be reflected in this staging area. So staging area, it's also known as the index. That part's not too important, but you might see it written as the index in other documents that you might read. But whenever you perform a git add, like I mentioned before, Git will take a snapshot of this file and record it to be backed up in the staging area. So let's see an example of that. We have our working directory, which is in orange. We have this wug.txt in here, and we also have a .git directory right over here inside the working directory, so you'll see it if you actually type ls-a in your own repository. But here's a .git directory, and here's a staging area. So when we type git add wug.txt, a snapshot of the wug.txt will be added to the staging area. So what that'll look like is some kind of representation like this. So wug.txt with hi is now in the staging area. All right, so notice that right now, this backup of wug.txt is not actually finalized yet. It's just living in the staging area. We haven't committed it yet, so it's just sitting here. But what do we call these snapshots? Because snapshot of wug.txt is kind of hard to say sometimes, and the terminology that Git actually likes to use is the word blob. So these snapshots are actually called blobs. So whenever I say blobs, these will refer to snapshots that Git has taken through git add. So blobs are the contents of a file at a given snapshot. So all of these, file A, A1, B1, B, all of these are blobs or snapshots of these files at certain times. Okay, so coming back to here, remember that after we have added this, it's just living in the staging area. This wug.txt is living here. But any change that we make to our working directory will not touch whatever is in the staging area. So here, if we try to modify wug.txt to include the word salutations or something, notice that the wug.txt here has not been changed. So it's just the same. We have wug.txt, same in the staging area, but the wug.txt in the working directory is different. Okay, so this is the second half of the permanently backing up process that we were talking about before. Whenever we perform a git commit, that is the completion of backup. All right, so whenever we do git commit, Git will move our blobs from the staging area into wherever it records all this information. It'll keep it for you forever. All right, so if we do git commit -m, this is our first commit. What that'll do is it'll make a commit that saves the wug.txt state when it was added, and then it'll clear the staging area. All right, so this is what it'll look like. We'll have the first commit made, commit 1, that's what we call the commit ID, description or the message that we did, which was first commit, and the files that we backed up. So it lists all the files that we have. So we have wug.txt here, and we've saved that blob into our .git directory somewhere. So now, staging area is clear. We kind of have this commit 1, first commit, and wug.txt as the files that are backed up. All right. So what happens if we try to add and commit a new version of wug.txt? So let's say we git add wug.txt one more time. We'll have salutations inside our staging area. And if we git commit -m with second, we create this new commit. This commit is the child of commit 1. So you see this back arrow pointing right here. The message is second, and the file is also wug.txt. But we have a problem here. We have wug.txt from commit 1. We also have a wug.txt from commit 2. But these are both having the same name, but different contents. Right? How do we keep track of a file that has the same name but changes throughout time? The answer to that actually is using this fancy word called content addressable storage. So the idea is that the names of these files are the same, but we know that the contents are going to be different. That's why that Git keeps track of them, because if it were the same, then they wouldn't need to have another version. The only reason why we have two wug.txts is because the content is different. So let's rely on the content to figure out what file that we're looking at. Right, so now the next question is, how can we convert file contents into a name? So the next solution that comes after that is actually hashing. So Matt mentioned it super briefly, but we're actually going to be talking about this a lot more in depth in the lab later on. But hashing, there's this thing called a hash function where it accepts any input and it converts it to this kind of string of letters and numbers. It's called a digest of fixed size. So this hash function will be used to summarize the data that we call the hash function on. And an object's hash function can be used to identify the content that has been hashed before. So like let's say you have this blob or something. You can hash this blob, get a string of letters and numbers that actually represents this blob. And any other blob with different contents will hash to something else. So all of these will hash to a different thing. So these are basically the IDs of whatever object that we're looking at. So that's why there's a fingerprint over here. That's kind of like the ID of a person, where a hash function is like an ID of the contents or whatever you're hashing. All right, so to get even more into the details, there is this specific hash function called the SHA-1 that you'll be seeing throughout the project. This is the hash function used by both Git and Gitlet. This one, it's just a special type of hash function that produces this special type of hash. So don't worry too much about the details, but for our purposes, we'll just interpret whatever this outputs as the name of our files that we're going to be hashing. So whenever we hash something, it'll look something like 73105AA, blah, blah, blah. It'll have all these different strings of letters and numbers, and that'll represent the object that we hashed. Every single object will hash to something else. So this is going to be basically the ID of what we're looking at. Okay, so we'll see there's utils.java file that is provided to you that has this in there, so you can just look in there for our version of the SHA-1. There is a small chance the SHA-1 produces the same hash for two different blobs. Just don't worry about that. Just let's pretend that doesn't work, or that doesn't happen, and just sweep that under the rug and just worry about the actual parts of the project. So this does happen in some cases that the SHAs can map to the same one. Just don't worry about that for this project, and just pretend that they're all going to be different IDs. All right, so now let's see how the SHA-1 can be useful here. So we can convert our two wug.txts. We can hash the contents of the files. So hi will hash to that string, salutations will hash that string, and we can actually name them these strings instead. So hi will be this string over here, salutations is this string over here. So inside our commit objects, instead of just having the name of whatever file that we're looking at, we can have the name that maps to whatever the ID is. So we'll know exactly if we have a wug.txt in this commit and the name of the file is A9 blah blah blah, we'll always pick this one and not this one over here. All right? Yeah, question?
For programming this internally and we want to access something, like does the SHA-1 refer directly to our file, or does it refer to the whole?
Okay, so the question was, does the SHA-1 refer to the file itself, or does it refer to the commit? Was that it? Okay, so that's a good question, and we'll actually see a little bit later about how that can be done. So we'll see it in a little bit, actually. Okay, yeah, so this is actually the next slide. You can identify commits in the same way. So we can identify blobs in one way. We can actually use this SHA to SHA objects themselves. So the commits will be SHA'd as well. So commits can be identified by the hash of their own contents. So the commits contents is the commit name or the commit message and the mapping of file to the SHA IDs. And these commits will have their own SHA IDs as well. So there's different levels in which you can SHA. It's up to your design about when you want to do it or how you want to do it. But note that this will be a good identifier for a commit as well. Okay, so this is where these crazy commit ID strings come from. So if you see in your Git log, you'll see commit with a bunch of random numbers. Git will be using the same thing, that the SHA-1 on the commit object to produce this value right here. So these are the IDs that you will be seeing, that you will also be producing in your project. Okay, so I talked a bunch. Does anyone have any questions about anything that we talked about before we move on to branching? All right, perfect. So you might not have seen this yet, but there is also this functionality in Git called branching. So branching will allow you to diverge from the main line of development and continue working without messing with that main line. So this is a lot of words, but just pretend that you're working on a project with your partner. You have your own take on how to implement linked lists, and they have their own take about how to implement linked lists. What you can do at that point is use this branching functionality to make two different roads in your history. So you can take your own road and implement your linked list deck your own way. Your partner can take your own road and implement it their own way. So this allows you to be a lot more experimental with your code if you want to, like if in case you have a different idea from your partner or if you have a different feature that you'd like to implement, this is what you would be using, is this branching thing. Right, so you can always merge your branch in later. If you figure out that your partner's implementation is better than your own, you can implement, or you can merge that back into the master, or you can choose to merge yours into master, either. So you can choose to merge stuff with the branches that you make. It's great for writing experimental code, but now we should try to figure out how this works, because in your Gitlet you will have to implement this functionality too. So we're going to talk a little bit about how branching works and what that does, down in the history, the low-level stuff here. Okay, so the first question is, what is a branch? So you probably have seen this word master already, but a branch is just a special name for a commit. Gitlet's default branch is called a master, so that's why you always see that word master everywhere. Master is just a branch, which is a special name for a commit. All right, so when you make a new commit, your branch pointer will also move forward with that commit. So here we had master point to this commit at first. When we made a new one, the master moved forward with it. We will always be indicating these new commits that are made with this red arrow as well. Okay, so you can also make new branches too. So master is the one that you're given by default, but you can make your own branches with the branch command. So this will create a new branch that points to the commit that you're currently on. So you might think, why is this even useful? We'll actually see in a little bit. So if we had done git branch testing, that would create a new branch called testing. It's basically a pointer to the current commit, so you have two different branches now pointing at the same place. All right, so we have a bunch of different branches, but how does Git know what branch that we're actually on? The answer to that question is that Git maintains another pointer that tells you which branch you're currently on. And this special pointer is called the head. So you might have seen head detached or whatever messages before when you've done some checkouts before. This is the head that they're talking about. Head is the pointer to the current branch that you're on. Head will also follow any future commits that you make. So currently, head is on master. All right, so we've seen this checkout command before, but when you check out to another branch, the only thing that changes is the head and the contents of your working directory, because those contents will be reflected to what that current commit looks like. So if we did git checkout testing, this head will now move to the testing branch, like that. So you might ask, why is this even helpful? Because they're pointing at the same thing right now, but we'll see in a little bit about how this can be useful in two different branching scenarios. All right, so further commits, like I mentioned, will now advance on the new checked out branch. So if we made a new commit here, the new commit, the testing branch will follow, the head branch will move with it as well, but notice that the master stays in the same place. So this is where the branching will kind of be, you'll see how it's useful here. All right, so we can resume progress on the main branch by checking out. So you can freely check out between branches as much as you want. So if you had done git checkout master, that'll move your head back to the master branch. All right, and just as I mentioned before, it'll also return your working directory to this state. So the repository will now look like what it looked like here and not what it looked like over here. All right, so git checkout master will move your head back as well as make those files what they look like in that commit. And if we wanted to make a new commit and our head was pointing to master, the new commit would actually make it branch like the name suggests. So we have two different branches. This is our main line. We have this master branch that's branching off here, and our testing branch that's branching off here. So you can see how we can actually have two separate lines of development this way that kind of go along together. All right, so just like I was talking about before too, that these branches can be merged back together using Git's merge command or Gitlet's merge command. Unfortunately, these two, Git and Gitlet, implement merge differently, so I'm not going to talk too much about how that'll look because it'll be different for both of them. But it's detailed in the spec how Gitlet's merge will behave very clearly, so you can just look there and figure out what to do in that case. Okay, so just a summary of everything we talked about. Git is a stream of snapshots. It's keeping track of everything through these snapshots. They're added to the staging area as blobs, so blobs are the snapshots, and they're added by the add command. Blobs are permanently backed up when they are committed, so when you type git commit, that's when they're fully added to your repository. Blobs and commits are addressed according to their SHA-1s of their content, so just remember SHA-1 to use that in your project. And commits in the staging area are responsible for remembering the correspondence between blobs and which files they correspond to. A branch is a special name for a commit. The head tells us which branch that we're currently on. And this is kind of the image that you should be having when you're thinking about all these commands. There's a working directory with your files in it. There's this .git directory that contains all this stuff in it that keeps track of everything for you. All right, so Git and Gitlet, they manage a whole bunch of information, and your job in Gitlet will essentially be to make this thing, this underlying .gitlet directory, which is the one that you will be doing. Okay, any questions before we talk about the next section, which is persistence? All right, perfect. So persistence, John was mentioning this a little bit before, but every command that you issue to Gitlet will go through the main method. So you might not have seen this kind of functionality before, but I'll actually show it to you using my personal implementation of Gitlet. So let's see. All right, so this is a directory. Don't worry too much about this, but the way that Gitlet is going to be called is in this way. So we'll have Java gitlet.main, and you'll be implementing, or you'll be putting in the commands right over here. So if I wanted to initialize a Git repository here, it's Java gitlet.main init. So nothing really happens because that's usually what happens when you init. But if you type status, you can see that it'll print out the status of your repository right now. So we're on the master branch, there are no stage files, no root files, and these two are left blank. All right? So you can actually, let's say I wanted to add a file. So before I do that, I'll show you what's inside the wug.txt file. So if we look inside wug.txt, you can see that there's the word hi in here. If you see the not wug, it also has salutations. But we can add things to our Gitlet repository. So if I wanted to add wug.txt, it'll look like that. And if we type status one more time, we'll see that we have a staged file here right now. All right, so this is just to show you how this project will be working. Every single time you make a call to Gitlet, it's essentially running the main, and then the main exits. All right, so java gitlet.main adds wug.txt, java gitlet.main commit, first commit. But just note that each of these commands will start a new Java process. So all the variables that are declared during this Java process will actually disappear once that is over. So at the beginning of init, you'll have some state. Once the init is done, that state will disappear because that main method has now been over. So your job is to figure out how you can save these files to persist through multiple calls to the Gitlet program. All right, so now how do we store all the progress that we've made? There's actually this really cool thing. We'll get to it a little bit, but I want to talk about the file system first. So Java can actually interact with your own file system. So file system is just like how your computer stores all your files, but it can interact with your file system using the file class. So there's a special class in Java. You can use them to represent a whole bunch of random different things, but one thing that may be important for this project is that you can represent a path to a file or a directory and see if that file or directory exists. So for example, if I wanted to see, like you can create a file that represents the path to my personal repo on my file system, and then you can figure out if it exists or not. So to access a file or directory, you must assemble the path to that file or directory using this file object. So you'll probably become really good friends with this class in the end because you'll have to use it a whole bunch to access all the blobs that you have, all the directories that you make. So definitely get used to all the documentation for this file because it'll be pretty helpful. All right, so here are just some ways that you can use this file class. So this is not the exhaustive list for all you'll be doing in this project, but note that you can get system.getProperty of the user directory, which will actually give you the current directory that you're in. So new file with this will give you a file object that represents that position. So you can say, oh, I want to append the word .gitlet right after that and make a gitlet directory. So you'll be probably doing this in your project as well, but just get familiar with the file class and what it can do, because it can make directories for you, it can delete objects or delete files for you, it can write objects for you. So just make sure that you really get familiar with this. Okay, so the file class, along with the methods we've provided in utils.java, they'll allow you to read and write data between the files. So there's a few like write contents, read contents in the utils.java file. So definitely use those if you're planning on doing some sort of writing and reading in that way. So these are actually going to be really helpful for saving your blob objects in the .gitlet directory, because writing your blobs will essentially be reading the bytes from one file and trying to write it somewhere else. So just like we were talking about before, there's a read contents, there's a write contents, so you can use those to help you read and write your blobs to different places. All right, so what about storing like more complicated information? So like commit objects, for example. Those don't really exist in like a byte format yet, so how do we even like save this state? How do we save the commit objects? Maybe we need to define like a commit file format or something. There's actually a more simple solution to this, and it's done through this thing called serialization. So it's a very special, very fancy, very long word for just converting a Java object into bytes. That's basically what serialization is it's taking a Java object and converting it to its byte format. All right, so just keep that in mind whenever you see serialization. That's what this means, is it's taking a commit class or a blob object or whatever object, like a dog or something, it takes that and converts it to bytes that you can read or write into files. Okay, so serialization will allow us to save our objects to disk, because when we save something into disk, we need the bytes. We can't just save a commit object to disk. So we need to convert the commits into bytes, and then we can write those to our file system. Okay, so the way that we can actually use this serialization is all we need to do is make the object implement the serializable interface. That's it. And then Java will handle all the magic that happens after that. But as long as you say like public class commit implement serializable, your commit will now be serializable, and you can do this with it. Right, so making an object implement this interface will allow you to convert an object into its byte representation, and it just works like magic. So don't worry too much about how it works, but it'll do this for you. So it'll make it really easy to track things like commits, because you can make the commit objects, convert them into bytes, and then write those bytes to your disk. All right, so just a few things to note is that serialization does follow like pointers. So if you have a commit object that has a pointer to another commit object, that's a pointer to another commit object, and so on, when you serialize one of them, it'll follow all of those and serialize all the things that are on the line, which might be too long based on the runtime constraints. So just keep this in mind when you're designing your commit object. You don't want to have too many pointers for it to follow, otherwise it'll take too long to serialize. So keep that in mind. Static variables are also not serialized, so those are ones that belong to the class. Right? Don't expect them to be serialized and deserialized when you do this with your commits. And lastly, all this code for saving and retrieving these serializable objects is actually available in the spec for you. The reason why we didn't include it in the utils file was because you can use this code in many different ways. You can take it just as is, you can make some modifications to it, but it's there in the spec for you to figure out if you want to use it this way or if you want to make any changes to it. But this is done for you in the spec, so just take a look there if you're wondering how you can do the serialization. Okay, so I think this is one thing I didn't mention earlier, but like what is deserialization? So we know that serializing is taking a Java object and converting it to bytes. Deserialization is just the opposite. So it takes the bytes and it converts it back to a Java object. So just use these two methods to help you write things and read things back from your disk. Okay, so now what classes should be serializable? Most of these decisions are up to you and your partner to figure out whether you should make something serializable or not. But just recall that we need to keep track of a few things inside our Gitlet repositories. So we need to keep track of the blobs, we need to keep track of the commits, branches, the head pointer, staging area, and maybe other metadata that you have in your own repository, right? But you just need to keep track of a lot of stuff. The design for this project is open-ended, but here are just some suggestions that we have for you. So if you represent parts of your project as certain classes like commit objects or staging area objects or blob objects or anything like that, you should probably make them serializable so you can really easily write those to your disk. Remember that there is only one staging area as well, so just keep that in mind when you're trying to decide whether to make a class for it or not. You can actually choose between two options for your blobs. So the blobs can actually be plain text files, because those are bytes, you can still read and write them. You don't have to do any serialization for that because those are already in the byte format. So you can choose to make them plain text files, or you can have it to be a Java object. It's up to you, but just make sure that if you do choose to make your blob a Java object, that you make it serializable as well. So serializable, if you ever need to write something that's a Java object, make it serializable. Likewise, for branches and the head pointer, those can be text files, those can be serializable objects, it's up to you. But just remember, make it serializable if you want to use a Java object. And lastly, you probably want at least one additional class to handle the Gitlet commands. So in general, the gitlet.main should have very little code in it. The main is what we've provided for you as the runner. So as we saw in the demonstration, everything is run through Java gitlet.main something. Right? The main is like the runner for your entire program, but you should probably have something that diverts. Like you don't want all your code inside the main class. You probably want to divert it to somewhere else that'll handle the work for you. Okay, so if you haven't looked at the skeleton that we provided for you yet, this is what is provided. So just as a note, we actually don't provide too much skeleton because this is mostly up to you to design, to figure out what classes you need, what methods you'll need, anything else that you'll possibly need, that's up to you. But we have provided this main to kind of keep everybody like on the same page, so all the Java programs or all the Gitlet programs can be run in the same way. So we have this main, we have public static void main string ... args. So you've probably seen this before in some of the previous projects, but this is how it'll be used in this project. So this syntax is to allow this main method to accept any number of strings as arguments. So for example, when we have the init command, that only has one argument, but the add command can have two because it has the word add and the file itself. Maybe you have a checkout to a different branch, or you have a merge to a different branch. You have a varying number of arguments, so you don't know how many arguments that will be here. But just remember that if we call something like java gitlet.main add wug.txt, string args will contain this information in it. So you can see that in this very first spot in the array, it'll always contain the command of what we're doing. So it'll be add, or it'll be init, or status, or log, or any of those commands that will be right over here. And any other commands that you might need will be listed in the second spot in the array. Similarly, for if we had commit with add wug, so we have two words, but they're surrounded by these quotes. What it'll actually look like in the args is this. So we have 0. The 0th argument is the word commit, but the first one is add wug. So if you put quotes around it, that'll be saved into the same like space in the args array, which would be pretty useful. So you don't have to like iterate through all the array to make the message together. All right. So just keep this in mind when you're doing your project. This is how we're going to be running your program. It's through this main class, through the main method, and you can start here. Everything will be, the command will be the 0th place, and anything else will be 1, 2, or 3, and so on. Okay? All right, so does anyone have any questions about anything we talked about related to Gitlet? Yeah?
On the spec, it talked about when you're coding, there could be commands that are dangerous. I was kind of confused what that meant.
Yeah, okay, that's a good question. So in the spec, it has the word dangerous everywhere for some reason. The reason why we put the word dangerous in there is because in your, this is a really good question, thank you, but in your program, you'll be having to remove and write files a whole bunch. If your remove goes wrong, like let's say you accidentally remove like the wrong path of the file, you can actually touch files that you don't want to touch. Like let's say you have your resume like stored somewhere, but you accidentally tell Gitlet to remove that. Like that's why this is called dangerous, because some programs or some commands require you to make modifications to the files and write over them or delete them or like change them to this version. So the reason why they're called dangerous is so that you just know and just be careful about when you delete and like when you try to overwrite stuff, because that might, if you do it wrong or if something goes wrong, you can actually edit stuff that you might really care about. Yeah, so that's what the dangerous means, is that this can potentially, if you implement it incorrectly, touch the rest of the files that you actually care about. So I would say that before you do any of the dangerous files, just push everything to Git so you don't accidentally delete something. Right, and another note, this is kind of unrelated, but you will have this program, it'll be saved in this Gitlet directory. So if we look over here, cd dot, if we look in here, oops. This is saved in a docket or in a Gitlet directory. All right, so all your code for this project will be saved in a Gitlet directory, but the place that you'll be saving your metadata will be called the .gitlet directory. So if you ever try to remove the .gitlet directory, please, please, please remember to put the dot in front of Gitlet. Otherwise, you'll be removing your actual code. So don't type in rm gitlet when you mean rm.gitlet, because you'll be touching very important files versus like the metadata that you did before. So just keep that in mind. Unfortunately, we can't really change it because it's kind of like, this is how it is, gitlet.git. Yeah, so just make sure that whenever you remove these files, that put the dot in front of it. That's all I ask of you. Please don't delete stuff that you really care about. All right? Okay, any other questions? All right, perfect. So we'll end about 7 minutes early, so feel free to head out now. But if you have any questions about anything, we'll be here, so feel free to come talk to us about anything. But otherwise, we'll see you next week.